Hello, everybody. Last unit 9, right? Well, maybe not the last one if we're skipping over kinetics, but the last one for us to go through together is unit 9. And I'm excited about unit 9 because we get to talk a little bit about batteries. And I think this unit does a really nice job of kind of putting a lot of stuff together that we have already talked about, especially a lot of thermo, hence application of thermodynamics. So in order for us to apply thermodynamics, there's something that we have to define first. And this is a new value. And I believe I started talking about this a little bit in class, but this new value is what we call entropy. And entropy is a thermodynamic quantity that measures how dispersed the energy of a system is. So it has to do with energy dispersal. However, I tend to think of entropy as something a little different. So yes, it is how dispersed the energy is, but entropy deals a lot with disorder. And it's how disordered a particular system is. Okay? How unorganized, we could say, a system is. So systems in the universe, including chemical reactions, tend to favor towards disorder. Things like to be disorderly. Things like to be disorganized. And for people, this is especially true. It's very easy for people to become disorganized because it doesn't take a lot of energy in order to just throw things in your bag or to throw things on your desk or to throw things on the floor of your room. It takes energy, however, to keep things nice and orderly. So the entropy of the universe is constantly increasing because the universe is constantly striving for more and more disorder. And this is something that we're going to look at with chemical reactions in this unit. This is a spontaneous process. So in order for something to become disorderly, it's spontaneous. I go into my bedroom, I throw something on the floor, right? It just happens. However, it requires work to clean up the mess on the floor, to clean up the papers on the desk. It takes work to organize them. This process, however, the process of becoming disorganized, or the process of doing work, does not have to necessarily mean fast. So we can be very slow with how we throw our things on the floor. A lot of times people take a little bit of time to unpack their things from a vacation. Not me. I am all about unpack the bag the minute we get home because I need to be back in my element. But sometimes it could take people a little bit of time to, become disorderly. It could also take time for people to complete the work. So your desk might be a mess for a week, kind of like how I am, and eventually it will get done. So when we talk about these processes, it doesn't necessarily have to be fast. And we're going to talk more about that fast part as we progress through this unit. So let's take a look at some changes in entropy. So entropy is denoted by a capital letter S. And of course, that delta means the change in entropy. So what's happening throughout all of these processes when they occur? We've already talked about changes in enthalpy. Okay, so if I have an exothermic reaction, my enthalpy is negative. And if I have an endothermic reaction, delta H is positive. In this case, we are going to put signs for delta S. What happens with entropy when entropy is increasing or when entropy is decreasing? Let's talk about solutions. So entropy, when we make solutions, increases. Why is that? Because the particles in a solute and a solvent disperse away from one another. When I make a solution, we already talked about this in thermo. When I put an ionic solid into water, I have to break ionic bonds and I have to break hydrogen bonds. And that system is becoming more dispersed in its energy. those ions are dispersing throughout the solution and it's becoming a little bit more disorganized. So entropy increases when we make a solution. It becomes more disorganized. Phase changes. So when I go from a solid to a liquid to a gas, entropy is increasing when changing state from solid to a liquid to gas. And that's because the particles become more dispersed when they occupy a larger volume. Gases are very far apart relative to their size, whereas solids are very tight and compact relative to their size. So because the gas particles are more dispersed from one another, they are farther away. That means that entropy is increasing when I go from solid to a liquid to a gas. It's all about dispersal of particles. In a solution, the particles disperse and entropy is increasing. When I make a gas, those particles are farther apart. Entropy is increasing. Also, an increase of volume of a gas also leads to an increase in entropy. So that's because if I have a container that's 1 liter versus I have a container that's 2 liter, let's just draw 1, 2, 3, 4, 5, 6 particles in here. 1, 2, 3, 4, 5, 6 particles in here. The particles in the larger volume are farther apart from one another. They are more dispersed. They're more dispersed away from one another. Therefore, the larger the volume means the more entropy that system has. Since temperature is a measure of kinetic energy, higher temperature gases have increased entropy. Are you catching the hint here? What's happening with all these values? When I increase kinetic energy, entropy is also increasing. When you are increasing the temperature or the kinetic energy, those particles are moving more. And if those particles are moving more, they're going to move a little bit farther away from one another. As a result, entropy is increasing. Lastly, entropy also increases when we have decomposition reactions, and that's because if I have one more complex molecule, let's take a look at NaOH. Okay, this, if we're talking about a decomposition reaction, this decomposes into Na2O and H2O. This is increasing in entropy. And that's because I'm breaking this down into smaller substances, into smaller pieces. As a result, the disorder is increasing. And what we say is that when entropy is increasing, our delta S is a positive value. Whereas if entropy is decreasing in a reaction or a physical process, the delta S is negative. So using all of that information, let's go ahead and do sample problem 1 together. So let's predict whether entropy is increasing or decreasing. And we'll also predict the sign of delta S. So let's try 1A together. So solid sugar is added to form water, or to water to form a solution. I'm making a solution here. I have some solid sugar particles that are very tightly packed together, and I'm going to add them to water molecules in a beaker. These sugar molecules are going to disperse away from one another in the system. As a result, entropy is increasing, and that means my delta S is a positive value. Okay. Again, it's all about energy dispersal or dispersal of the particles. It's more disorderly, right? Usually we like to have things in an orderly pattern. So ionic solids like to be together. But when they're introduced to water, they like to become separated because, of course, they want to be as far apart from one another because of their entropy change. Iodine vapor condenses on a cold surface to form crystals. So here I have iodine vapor, so I2 gas, is condensing to form crystals. So actually we're going to do, I'm not going to say condenses. I'm going to say gas to a solid is a deposition. So solid right there. In this case, I have particles that are really far apart relative to their size going to solid iodine right there. In this case, entropy is decreasing. The particles are not as dispersed after this process. So my delta H is going to, or my delta S, I'm sorry, is going to be a negative value. So the following reaction represents the essential change that takes place during the fermentation of glucose into ethanol. So this is essentially how they would make wine and beer. They take glucose and it breaks down into a variety of chemical reactions, but ultimately you get ethanol and carbon dioxide. So this is a nice decomposition reaction. Okay, so I got a decomposition. I have 1 mole of glucose that's breaking down into 2 moles of ethanol and 2 moles of CO2. So I have 4 moles of products total. If I'm producing more products, this has an increase in entropy. My delta S is going to be positive. Things like to break down. Okay, so because it's breaking down, the entropy of the system is increasing. Let's take a look here. I have ammonia gas, 2 moles of ammonia gas, 1 mole of CO2. I have some aqueous, whatever this is, and I have some liquid water at the end of this. So there's a lot of different factors you can really consider. The first thing is you can look at the number of particles. So here I have 3 moles of particles total, becoming 2 moles of particles. So this is not a decomposition reaction. In fact, some of these smaller molecules are coming together to form something more complex. Not only that, but all the moles of reactants are gases in my reactant side. On my product side, I have an aqueous species and I have a liquid. So no matter how you look at this, the entropy of this system must be decreasing. This is really not an entropically favorable reaction. This reaction may occur, but it might not occur as a result of entropy changes. And that's something we're going to consider. So my delta S here is going to be negative. Let's take a look at E. So looks like I have carbon monoxide and water, both gases, 2 moles, produces CO2 and H2, also 2 moles, also both gases. In this case, my delta S is actually not changing. The entropy of the system is the same, right? And that's because I have the same number of moles of gas in my reactants as I have in the products. I have 2 moles of gaseous reactants and 2 moles of gaseous products. Entropy is not changing as a result of this. In this case, I have CS2 liquid. So if I draw a beaker, right, liquids take the shape of the container that they're in. But if I have CO2 gas, these particles become very far apart. What can I say about entropy? Because those particles are far apart, entropy is increasing and delta S is positive. This would be a great example of a question that College Board would ask you. It's just what is going to be the sign of delta S? So it would say positive or negative, and then you would have to explain why. So that would give you 4 options for multiple choice questions. What we can do is what we did here. We predicted the sign for entropy. However, not only can we predict the sign, but we can also actually calculate a numerical value for entropy. Okay, how much is entropy increasing or decreasing in a reaction? And that green paper that I gave you has all of these delta S values on it. But in this packet, I tried to give you those values like they would on College Board, so you don't have to go searching for each of these entropy values. Anyway, reaction is just like the one you saw in Unit 6. So if you remember, the delta H of a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. It's the same exact equation for entropy. So the change in entropy throughout a reaction or a chemical process or a physical process is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. And we're given all of these entropy values down below for sample problem 2. So let's calculate delta S at 25 degrees given the standard entropy values. So my delta S for this reaction is equal to, let's get the products down first. SO2 has a delta S of 248. So it's 248. Notice the units for this are a little different. Joules per mole Kelvin. And we're going to times that by however many are here. So there's 2 moles of SO2. We're going to add that to NiO. NiO has a delta S of 38. So we have 38 joules per mole Kelvin times that guy by 2. So here's everything for my products. I'm going to subtract from that the sum of the reactants. So I have 2 NiS's, nickel 2 sulfides. 53 is the delta S, joules per mole Kelvin, times 2. And I'm going to add to that my oxygen. Oxygen does have a delta S value. It is 205 joules per mole Kelvin, but there are 3 of them. Remember, all of these values technically are 3 moles. So when you do this work right here, moles on the denominator for your entropy cancels out with moles because that's in the numerator of that number of moles. And when you solve for this, if you solve for it correctly, so what I recommend doing, do this step by step. Do not type this all in one line in your calculator. I personally would do this first, that first, and that first. Then I would add these together, and then I would add these together, and then I would do the subtraction at the end. If you do the math correctly, you're left with negative 149 units for entropy are joules per Kelvin. So if I look here, because moles, everything technically canceled out, you're left with joules per Kelvin. So this reaction would have a negative value for delta S. So this is not really an entropically favored reaction. This reaction may occur even though it's decreasing in entropy, okay? Something else must be driving this reaction to occur, which again, we'll talk about in the next video, actually. Let's try another one here. So same exact deal, calculate delta S. Here we go. Delta S is equal to the sum of the products. So I have aluminum as a product. Just make sure you find the right one. Looks like it's 28 joules per mole Kelvin. Oops, forgot an L. Times 2. Plus, I have gaseous water, 189 joules per mole Kelvin, times 3, minus, let's do my reactants, aluminum oxide is 51, and there's only one of them, so I'll just do times 1, plus my hydrogen gas is 131, and there are 3 of them. Again, take this step by step, right? Each individual step. Answer should be, if you do this correctly, you get positive 179 joules per Kelvin as your entropy value. So in this case, entropy is increasing for this reaction. So delta S is a positive value. So like I said, we can determine just the sign for entropy, but we can also quantitatively calculate this by using this equation up here, which you'll be given these charts on College Board, just like I gave you here. What I'm going to do is I'm going to actually skip a couple of pages because I want to go past Gibbs free energy, and I just want to talk about entropy in this video. So we are going to skip to page 8. So let's skip over all this Gibbs free energy stuff. I'm going to go right to 8. So let's talk about that entropy change for a phase change. We've already established that gases have the highest amount of energy. So as I go from a solid to a gas, right, delta S is going to be a positive value. As I'm going in this direction, delta S is going to be a negative value. So my highest entropy deals with gases, and my lowest entropy deals with solids, okay? So since entropy changes whenever there's a phase change, the change in entropy is equal to the heat added divided by the temperature at which the change took place, okay? Sometimes I kind of have a hard time wrapping my head around this, and I didn't teach this last year. So I'm going to try my best to explain this in the video because it has been a long time since I've talked about this. But we can do sample problem 9 and 10, and then we'll be done with this video. So my entropy value, so because entropy has units of joules per Kelvin, okay? So if I look here back at these problems, when we calculated entropy for a reaction has units of joules per Kelvin. So if I want to calculate what is the entropy for a phase change, I can easily calculate that by looking at, okay, what is the heat that's associated with that phase change? Because heat tends to be in units of joules or kilojoules. If you think back to, because remember, Q is equal to H in this case. So it's the enthalpy of the reaction in units of joules or kilojoules divided by its temperature, okay? Where Q is equal to, because we're dealing with a phase change here, okay? That Q is going to be equal to either one of those two values, your enthalpy of vaporization, depending on if I'm going from a liquid to a gas or a gas to a liquid, or it will be equal to my enthalpy of fusion, which would be or going from a solid to a liquid or a liquid to a solid. In the rare case, you might see an enthalpy of sublimation that would go from a solid to a gas or a gas to a solid, okay? But we don't typically deal with those. So let's calculate what's the entropy of 1 mole of the vapor in equilibrium with the liquid. So we have the heat of vaporization for carbon tetrachloride. It takes 39.4 kilojoules of energy to vaporize 1 mole of carbon tetrachloride, okay? And we want to know what's the entropy of this. What's the entropy change in this case? We can infer that entropy should be a positive value, okay? And that's because we are going from a liquid to a gas. That makes sense. However, what is the numerical quantity of that value? That's what we're going to calculate here. So we have our enthalpy of vaporization. Okay, it's equal to 39.4 kilojoules per mole. This reaction is asking us for 1 mole of liquid carbon tetrachloride. So because we're asking for 1 mole of this, and I have, in this case, so I have 1 mole of liquid carbon tetrachloride has an entropy of 216 joules per Kelvin. What is the entropy of 1 mole of the vapor in equilibrium with its gas? So it's saying that at this temperature, I have these two species that are in equilibrium with one another, okay? And I want to know what's the total entropy of that system. So the heat of vaporization is equal to 39.4. That's per 1 mole. And this reaction here tells me I have 1 mole of the vapor. So if I am vaporizing 1 mole of this, I would have 39.4 kilojoules of energy that's required to do that. So my Q in this case is going to be 39.4 kilojoules. Q is equal to that. But to calculate entropy, we want this value in units of joules. So I'm going to do 39,400 joules. This particular process, this vaporization process, is happening at 25 degrees Celsius. So 25 degrees Celsius is equal to 298 Kelvin. This is going to give me my entropy for that gaseous carbon tetrachloride. So my gaseous carbon tetrachloride would have an entropy of positive 132 joules per Kelvin. We want to know, though, what is the total entropy of this equilibrium? So I have both of these species that are present in the system. To find the entropy at equilibrium, because they're both there, I would take that 216 joules per Kelvin of its entropy, and I'm going to add that to 132 joules per Kelvin. And that's going to give me a value of 348 joules per Kelvin. So this entire process, this equilibrium, has an entropy that is positive 348 joules per Kelvin. Okay, that's what we're calculating, is how much entropy is changing during a phase change. Okay, we're putting a quantitative value to that. Let's try sample problem 10, and then we'll be done. So liquid ethanol, this is a problem that is just like this. And honestly, these types of problems are the only ones I've seen that you would encounter on your exam. But you do need to know this little equation. And I think it makes sense because entropy has units of joules per Kelvin, right? Heat divided by temperature gives you joules per Kelvin, okay? It's a pretty self-explanatory equation there. Though the math, sometimes it's kind of like, I still haven't totally wrapped my head around how this works, though I could do the calculations, okay? Sometimes that's all we have to do is just do the darn calculations, right? You don't have to, we'd have to know the ins and outs of everything that we do. That's why I have college professors. They'll be able to help you. Liquid ethanol, it's in equilibrium with its gas. So liquid ethanol at 25 degrees has an entropy of 161 joules per mole Kelvin. If the heat of vaporization, so delta H vape, is equal to 42.6 kilojoules per mole, what is the entropy of the vapor? So we want to know delta S is equal to what? That's in equilibrium with the liquid. So I want to know what's the total delta S in this case. So we're only dealing with 1 mole in this case because I have 1 mole of this and 1 mole of this. So technically, because it's already for 1 mole, we're just going to say 42.6 because that gives me units of kilojoules. So that's the top part of my entropy value. So let's calculate this guy right here. So my delta H or my delta S for gaseous ethanol, delta S is equal to the heat that's required to vaporize that. So let's convert that to joules, 42600 joules. And this is occurring at, again, 25 degrees. So that's 298 Kelvin. Do the math, I get 143 joules per Kelvin. So delta H here, or delta S, I keep saying delta H, is 143 joules per Kelvin. I want to know what's the entropy of the vapor in equilibrium with the system. So because it's in equilibrium, I want to add these two guys together. So 161 joules per Kelvin plus 143 joules per Kelvin gives me 304 joules per Kelvin. That is the entropy that's associated with ethanol in equilibrium, a liquid between its gas. Again, let's just get the basics of this equation down. You might see one question on this, right? This is no buffer question. You're going to have lots of questions on buffers. You're not going to have a lot of questions on calculating delta S for a phase change. If you want more help, of course, you can always look at the I do, we do, you do for that. Otherwise, that's it for this video all about entropy. Looks like it was pretty short if I'm looking at the time. Otherwise, I will see you in the next video, which we're going to take entropy, combine it with enthalpy, and get a new value that's much better to determine how favorable a reaction is. And that's our Gibbs free energy value. So I'm not going to talk about it anymore. I'll talk about it then. Have a great day. Bye.